Okay, so the root mean square error, so the logic is that it measures error. It measures the root of the mean of the squared error. It's a lot of statistics, all right? So because it measures error, now it's the lesser the number, the better your model, because it measures error. It makes sense if your error is 0 or your error is 0.7, your error is 1.2. The lesser it is, the better. All right. So now to so we have the linear regression, which has been imputed, which has been imputed from the start. So we assign it to LN model. So every time we use LIN_model, what we are using is the linear regression model. So this is the linear regression model, like an empty model without data. So the next thing is to now fit in the data into the model by saying lin_model.fit. Then we bring in the X train and the Y train, right? The independent variables for the training sets, the dependent variable for the for the training sets as well. Now they will make predictions. We say linear prediction. We predict the X tests. We train the X train, so we now predict the X test. So it generates Y tests for this particular X test. The Y_tests was not given here, was not stated in this prediction. That's because we are only giving it the X so that it can predict the Y. Now, once it predicts the Y, that is where the evaluation comes from. Then we evaluate it by saying we have the Y test and the linear prediction. Then we get the square roots of the mean of the error. So the error is, the error is when you have your prediction minus the tests, or the test minus the prediction, because we now modulize it, we turn it, we multiply square root of it makes it positive, so then we run the evaluations. We try to test how good are the models. So you see the first one, the linear regression, which is the accuracy score. You remember I said as it tends to 1, the better. We have 0.45. So it still signifies that this accuracy is around guessing stage. The prediction is still like guessing, still a 50-50 thing. The accuracy is saying that 55% it gets it correctly, 45% it gets it wrongly. While for the RMSE, you can see it still hovers around the guessing stage, because this is 53. So it's like 53 over 100, 53 error, 53% error, and the other 40-something% accurate, which is what we have also gotten in the linear regression. All right. So another model is the decision tree. For the decision tree, we have for the linear model, we have linear model and then the empty brackets. Here we have the random state equals 42. This random state is just to ensure that we both get the same answers. All right. It can be blank as well. Then we have train model. That is where the model is. Now to train the model, we just write train model.fit, then X train, Y train. Can you see the pattern? You have the X train and the Y train. Then to make the prediction again, we have the tree prediction. Then we have predicts X tests rather. Sorry. Now then we evaluate just the same thing. Then we run it again. So here, this drives further, is a smaller accuracy. Yeah, smaller accuracy, and then higher RMSE, which is still almost telling us the same story. So, I said accuracy, the more it tends to 1, the better it is. Now, this is even less than 0.01. So that means that the regression model is still better than the decision tree for this particular data. All right. The third one is the random forest regressor. The random forest regressor will do the same thing. The first thing, the empty model, we assign it into an object. You can see RF underscore model, RF meaning random forest. Then we fit it, RF underscore model fits X train, Y train. We do this by telling the computer to learn it, to master it, to master this particular data. All right, then make predictions. Then we tell it to predict only X tests. We will not show it the Y tests. Then again, to evaluate the model, we evaluate how good has the prediction be. When we did not give it the Y test, it was able to predict it very well. So Y test and then the prediction. Then it checks the differences and squares them up and does the square roots and all of that. Then we get the accuracy and the RMSE, which, let's see if this is a better model. So this is 0.44 and 54. Again, let's go and check the regression and see if we had the same thing for the regression model. 0.45 and 53. All right, so 0.45 is better than 0.44, although it's by 0.01, so but still something. All right, so from the 3 models, we have seen that the regression model gave us better. Now, it does not mean that when we try another data with these codes, it does not mean that that regression will be better. Sometimes, or most times, random forest is a stronger model than the regression and other models. All right, so once we've done this, we would want to put our models in the same table to compare, to have everything together compared. So let's see what we have. For the linear regression, the accuracy score is 0.45, the RMSE is 53. So here we look at which one is closer to 1, is closest to 1, which is linear regression. Here we look at this column, we look at which of these entries are tending to 0. It's 53. So here we say that regression model is still the best out of the 3. So there are some other things that we can do to make this model better, but as an introductory lesson, it's okay. Then we plot it again. We plot what we have seen there. So you see that this is the R square. The R square, we want it to tend to 1. Don't forget, it's the accuracy score. But this decision tree has the least. It performed the poorest. However, there is rivalry between linear regression and random forest. All right, so you can always pick on another data and then just pass it into this pipeline and do everything. Just manipulate the data and then you get the same. You get your own answer. For different data, you get different responses. All right, so thank you, and that will be all on regression supervised learning.